We have already introduced three state functions describing the state of thermodynamic systems: the internal energy, enthalpy, and entropy of a system. The state functions, also called thermodynamic potentials, are completely determined by the state P of a thermodynamic system. That is, they are unique functions of the state variables x1, x2, ellipsis, xn describing the state of the system, as seen here in the case of the internal energy U. If the system is brought from an initial state P0 to the state P during a thermodynamic process along a path calligraphic P in the state space, then the change in its state functions, for example the change in its internal energy U, depends only on the initial and final states of the process, and is independent of the path calligraphic P. In other words, the infinitesimal change in the state functions is an exact differential, that is, the differential of U is exact. Besides internal energy, entropy, and enthalpy, there are two other state functions in thermodynamic providing more information on the state of a system. The first one is introduced by Helmholtz, and it is called Helmholtz free energy. In order to define free energy, we write the first law of thermodynamics in a differential form, stating that the infinitesimal change in the internal energy U of a system is equal to the sum of the infinitesimal amount of heat Q exchanged between the system and its surroundings and the infinitesimal amount of work W done during the heat exchange. When we talk about the expansion or the contraction of the volume of the system, as in the case of an ideal gas warmed up or cooled down, we can write the infinitesimal work as the pressure volume work given by minus the pressure P of the gas times the infinitesimal change in the volume V of the gas. The second law of thermodynamics states that the infinitesimal amount of heat Q exchanged between the system and its surroundings is less than or equal to the temperature T of the system times the infinitesimal change in its entropy S, depending on whether the process of the heat transfer is irreversible or reversible. If we substitute the second law in the first one, we can write that the differential of the internal energy U is less than or equal to the temperature T times the differential of the entropy S, plus the infinitesimal amount of work W, or T times ds minus the pressure P times the differential of the volume V. In the case of an isothermal process, the temperature T of the system is constant, and the differentials can formally be factored out from the difference between du and T times ds if we reorder the terms in the inequality. As a result, the differential of the difference between the internal energy U and the product of the temperature T and the entropy S is less than or equal to the infinitesimal work W, or minus the pressure P times the differential of the volume V. Helmholtz used the expression in the parenthesis, that is the internal energy U minus the product of the absolute temperature T and the entropy S, when he defined a new state function called free energy F in 1883. By virtue of the first law, we already decomposed the internal energy U of a thermodynamic system to the sum of the heat Q transferred to or from the system, and the work W done on the system. The choice of the name free energy indicates that the internal energy U of a thermodynamic system can also be interpreted as the sum of the free energy F, and the bound energy of the system given by the product of its temperature T and entropy S. Now we will explain why free energy can be considered as a free form of energy, and why the product of the temperature and the entropy represents a bound form of it. We saw that the differential of the internal energy U minus the temperature T times the entropy S is less than or equal to the infinitesimal amount of work W done on the system. By applying the definition of free energy, we can state that the production of the free energy F given by its differential is less than or equal to the infinitesimal work W done on the system. The latter is equal to minus the infinitesimal work W prime done by the system, as seen in the figure with the sign convention for the direction of the energy transfer in the form of heat and work between a thermodynamic system and its surroundings. Then we can state that the infinitesimal decrease in the free energy F is greater than or equal to the infinitesimal work W prime done by the system. This inequality can also be written with finite differences stating that the decrease in the free energy F of the system brought from the state 1 to the state 2 is greater than or equal to the work W prime done by the system. As a result, the maximum infinitesimal work W prime done by the system is equal to the negative infinitesimal change in the free energy F of the system. In other words, the decrease in the free energy of a thermodynamic system measures the maximum work that can be done by the system during an isothermal process in a reversible limit. By virtue of the first law, the infinitesimal decrease in the total internal energy U is given by minus the infinitesimal amount of heat Q absorbed by the system, minus the infinitesimal amount of work W done on the system. As the figure shows, minus the heat Q absorbed by the system is equal to the heat Q prime discarded by the system, and minus the work W done on the system is equal to the work W prime done by the system. At the same time, we can use the definition of free energy and write the infinitesimal decrease in internal energy U as minus the differential of the sum of the free energy F and the product of the temperature T and the entropy S, which is equal to minus the differential of the free energy F, minus the differential of the product of the temperature T and the entropy S. By eliminating the differential of the internal energy U from these two expressions, we obtain an equation stating that sum of dq prime and dw prime is equal to minus dF minus the differential of the product of T times S. We already saw that minus the differential of the free energy F is greater than or equal to the infinitesimal work W prime. Then it follows from this inequality in the equation that minus the differential of the product of the absolute temperature T of a system and its entropy S must be less than or equal to the infinitesimal amount of heat Q prime discarded by the system. This result shows that in an isothermal process, the free energy of the system is the maximum amount of energy from its total internal energy which can be converted to useful work. The rest of the internal energy represented by the bound energy of the system, that is the product of its temperature and its entropy, is minimally released in the form of heat by the system. As an example, we will determine the free energy of an ideal gas in a final state of a thermodynamic process. A given amount of gas can expand from an initial state A with the temperature T0 and the volume V0 to a state B with the temperature T and the volume V, by absorbing some heat Q from its surroundings while doing some work W prime on it. We already derived the entropy production in a transformation between the states A and B, and we found that it is equal to the mass m of the gas times the sum of the heat capacity CV of the gas at constant volume times the natural logarithm of the ratio of T to T0, and the specific heat capacity Rs of the gas times the natural logarithm of the ratio of V to V0. We can choose the initial state A as a zero state, where the entropy S of the gas is set to zero. We also note that the internal energy U of an ideal gas is given by its mass m times its specific heat capacity CV times its absolute temperature T. The expressions of entropy and internal energy can be substituted in the free energy F of the gas defined by its internal energy U, minus the product of its temperature T and entropy S. Then we can write that F is equal to the mass m of the gas, times the quantity of the specific heat capacity CV of the gas times its temperature T, minus the specific heat capacity CV of the gas times its temperature T times the natural logarithm of the ratio of the temperature T to the temperature T0, minus its specific gas constant Rs times the temperature T times the natural logarithm of the ratio of the volume V of the gas to the volume V0 of the gas at the temperature T0. If the gas undergoes an isothermal expansion, that is, it increases its volume from V0 to V at a constant temperature, then the decrease in the free energy of the gas is equal to its mass m times its specific gas constant Rs times its constant temperature T, times the natural logarithm of the ratio of the volume V to the volume V0. The product m times Rs can also be written as the amount of species n of the gas times the universal gas constant R, and the whole expression is equal to the work W prime of an expanding ideal gas in a reversible process, as we expected. We already saw that the entropy in an isolated system increases during irreversible processes in nature. Since there is no exchange of energy in the form of heat or work between an isolated system and its surrounding, there is no change in the internal energy of such a system either. Then the statement on the entropy production in an isolated system immediately follows from the combined form of the first and the second laws of thermodynamics, stating that the differential of the internal energy U of the system is less than or equal to its absolute temperature T times the differential of its entropy S, plus the infinitesimal work W done on the system. This inequality reduces to the one stating that T times ds is greater than or equal to 0 because both du and dw vanish for an isolated system. Since the absolute temperature T is non-negative, the differential of the entropy S of an isolated system is greater than or equal to 0. In the case of non-isolated systems, the exchange of energy is allowed between the system and its surroundings, at least in the form of heat. We introduced free energy for isothermal processes, and now we suppose the process is isochoric as well. Then the infinitesimal change in both the temperature T and the volume V of the system vanishes. We can apply the inequality obtained for the decrease of the free energy in the form stating that the differential of the free energy F is less than or equal to the infinitesimal work W prime done by the system. The latter represents the pressure volume work given by the product of the pressure P of the working substance and the infinitesimal change in its volume V. Since dV is 0, we can write that the differential of the free energy F is less than or equal to 0. Then we conclude that in an isothermal and isochoric process, the Helmholtz free energy of a thermodynamic system decreases until the system reaches equilibrium, and the free energy attains its minimum. In other words, thermodynamic processes in a system minimize its free energy under constant temperature and constant volume. The last state function introduced by Gibbs is called free enthalpy or Gibbs potential, and its definition is analogous with the one of free energy in a thermodynamic system with a given internal energy U and entropy S. We already used the combined formula of the first and second laws of thermodynamics stating that the differential of the internal energy U is less than or equal to the temperature T of the system times the differential of the entropy S plus the infinitesimal work W done on the system. Here the infinitesimal amount of heat Q absorbed by the system is less than or equal to T times ds due to the second law. We usually consider the work W as the pressure volume work given by minus the pressure P of the system times the differential of its volume V, but now we include the infinitesimal work associated with some chemical potential, or done by electromagnetic or other external forces. For the sake of brevity, let Wx denote the net work done by all these various types of forces. If we reorder the inequality, we can write that the differential of the internal energy U, plus the pressure P times the differential of the volume V, minus the temperature T times the differential of the entropy S is less than or equal to the infinitesimal work Wx done by the various types of forces. For isothermal and isobaric processes, the differentials of the temperature T and the pressure P vanish. Since the pressure P is constant during the process, the pressure P times the differential of the volume V can be written as the differential of the product of the pressure P and the volume V. Then the differential can be factored out from the left-hand side of the inequality, and we can state that the differential of the three terms, that is the internal energy U, plus the pressure P times the volume V, minus the temperature T times the entropy S is less than or equal to the infinitesimal work Wx. Here the sum of the internal energy U and the product of the pressure P and the volume V is defined as the enthalpy H of the system, and the left-hand side of the inequality can be written as the differential of the difference between the enthalpy H and the product of the temperature T and the entropy S. We have already shown that the product of the temperature and the entropy represents a bound energy stored in a thermodynamic system, which motivated Helmholtz to define free energy. Similarly, in the early 1870s, Gibbs introduced another thermodynamic potential or state function called free enthalpy or Gibbs potential. The free enthalpy G is defined by the enthalpy H minus the product of the temperature T and the entropy S. This definition can also be written as the internal energy U, plus the pressure P times the volume V, minus the temperature T times the entropy S. It follows from the definition that the SI unit of the free enthalpy G is joule, that is, it has a dimension of energy. This thermodynamic potential is also known as Gibbs free energy, but we will use the phrase free enthalpy to avoid its confusion with Helmholtz free energy, which we simply call free energy. As in the case of the internal energy U, the introduction of a free quantity allows us to decompose the enthalpy H in two different ways. On the one hand, the enthalpy H is defined by the sum of the internal energy U and the product of the pressure P and the volume V. On the other hand, the enthalpy H can be written as the sum of the free enthalpy G and the product of the temperature T and the entropy S, which plays the role of the bound form of the enthalpy now. By applying the definition of free enthalpy, we can write the original inequality as the one stating that the differential of the free enthalpy G is less than or equal to the infinitesimal work Wx done on the system by the various types of forces. The latter is equal to the work W'x done against these forces by the system, and we find that the negative infinitesimal change in the free enthalpy G of the system is greater than or equal to the infinitesimal work W'x done by the system. As a result, the maximum amount of work Wx' done by the system is equal to the decrease in the free enthalpy G of the system. In other words, the decrease in the free enthalpy of a thermodynamic system measures the maximum work apart from the pressure volume work that can be done by the system on its surroundings during an isothermal and isobaric process in a reversible limit. If there are no chemical reactions in the system or no electromagnetic or external forces act on it, then the work minus dW'x vanishes and the infinitesimal change in the free enthalpy G is less than or equal to zero. Then we conclude that in an isothermal and isobaric process, the free enthalpy of a thermodynamic system decreases until the system reaches equilibrium, and the free enthalpy attains its minimum. In other words, thermodynamic processes in a system minimize its free enthalpy or Gibbs potential under constant temperature and constant pressure.